Mathematically, the mechanical work done by a force on an object is the product, okay, product being multiply, of the magnitude of the force, right? So how big the force is, and then the displacement of the object, which kind of takes the direction, right? Because displacement is a vector. Okay, and if I were to write the equation for work based on those words, I'd get work is equal to the force applied multiplied by the displacement, delta D. Okay? And this equation only applies to situations where the magnitude of the force and the displacement are in the same direction. Okay, so work is a scalar quantity. There's no direction associated with work, hence the absence of the vector notation in the equation above, right? And vector notation means that, right? So we don't have that because it's a scalar quantity, okay? Like distance. So the units for work is the Newton meter, which looks like this. Newton meter, so it's newtons times meters. If you guys were to look at the units on here, newtons, and you're multiplying by meters, so the dimension says that it's Newton meters, not newtons per meter. Okay, that's different. Okay, so it's the Newton meter, and 1 Newton meter is equal to 1 joule of energy, we'll say. Okay, so one thing to notice is we don't take into consideration the amount of time that a force acts on an object, right? Or the velocities or accelerations. Just here's the force being applied. How much distance or displacement does it cause something to move, right? And that would be the work. Okay. So the first question, we'll start easy. How much mechanical work does a store manager do on a grocery cart if she applies a force of 25 newtons in the forward direction and displaces the cart 3.5 meters in the same direction? Okay. Well, we know that the force is equal to 25 newtons and that the displacement is 3.5 meters. And so work tells us that we take the force and we multiply by the distance or displacement. Right? And we're going to see, we just plug in the numbers. 25 newtons multiplied by 3.5 meters is going to equal 88. What are the units? Newton meter. What did we say a Newton meter was? A joule. 88 joules. So 88 joules of or work was done. Okay, that's an easy one. Okay. But what if I throw a wrench in things? And this is like, I don't know, I like physics from this standpoint. It's a little bit better than math from the standpoint that like there are connections in math that you need. But with physics, we can always go back to the previous unit. And so I like the start of this unit is cool because we have like forces still. So we can use all this like knowledge from the last unit. But we can also infuse some kinematic stuff like this question, right? So a curler applies a force of 15 newtons on a curling stone and accelerates the stone from rest to a speed of 8 meters per second in 3.5 seconds. Okay. Assuming that the ice surface is level and frictionless, how much mechanical work does the curler do on the stone? Okay, so this is what I mean. If you guys have left the question blank on your test, this is what I'm talking about, right? Like I'm going to give you a half mark to extract the information, right? So just something as like as simple as a list of knowns and unknowns. Like I just want to see that so that I at least know that you guys know what a Newton is or like meters per second. Like you're associating meters per second with velocity and seconds with time and newtons with force, okay? So if I were to write out all this stuff here, right, like I'd be able to say, okay, well, I know the force is 15 newtons, right? I know the final velocity is 8 meters per second. I know t is 3.5 seconds, right? And we also know one other thing. Stone starts from rest, so v1 is equal to 0. Right? Being able to do this is a critical part of a question. Just knowing that you know the velocity is meters per second and t is time, like seconds, v is, you know what I'm saying? It's an important part of the question. Like, you can't solve this question if you don't know what it is you're given and what it is you're looking for, right? That's difficult to do, right? Then I'd say, okay, well, here's another mark for the question is like, okay, well, which your like analysis or like selection of a tool, right? Of what you're going to solve with, right? Well, I know that this question's asking me for how much work. So I'm going to want to use the work equation, force times, like we'll call it delta D or displacement. Okay. And, okay, well, that's not too helpful because nothing in this question has told me what the displacement is. But the question did give me enough information to do a workaround calculation to find what that delta D value is using one of the kinematic equations that you guys already know from your formula sheet, right? Like we know that delta D is going to be equal to V1 plus V2 divided by 2. And if we multiply that by T, or the change in time, we can find what the displacement value is, right? Well, it looks like I know V1, I know V2, I know delta T, so I can find this delta D value and plug it in there, right? Or, if you're feeling really fancy, if you know that delta D is this, then why don't you replace delta D with all of this? Or another word for that is substitute. Right? Where do you substitute it? Right here. So what's work equal to? Well, work is equal to force times V1 plus V2 divided by 2 delta T. Maybe I'll put that in square brackets to explicitly show that D, or delta D, the displacement, is everything inside of the square brackets. Right? So now we can just plug in our information, right? And find what the work value is. Well, we know that the force from our list of knowns was 15 newtons. So 15, right? And what goes on the inside? Well, V1 was 0 plus 8 for V2 divided by 2. And then we're going to multiply that by the 3.5. So what do we get? 8 divided by 2 is 4 times 3.5. And we just do the math. So you should find that the work will be 210 joules. Okay? Anybody have any questions? Okay, this is, I'm trying to emphasize the fact that if you guys write this down and you know the equation for work, you're going to try and, oh, I have a problem. Yes, you have a problem. You don't know delta D. That's physics. Physics is about figuring out what's the workaround. This is the workaround over here. You know something for delta D. You can substitute it in there. Right? And that's your workaround. We don't explicitly need to tell you every single number. I can give you other information, right? Because sometimes if you're in the real world doing some of these problems, like if you're an engineer, there's only something, like some things are unmeasurable, right? But other things are. And so if we're able to actually record data and measure things, then we can use that data to solve for the thing that we don't know or that we can't measure. It's an intangible thing, right? That's what this is all about. And so this is a big part of the question, right? And so I'm giving half marks for that, and then I'm giving half mark for that, and I don't know, trying to be as generous, but still like, it's not just about the final answer. It's about your process and working around, like your thought, right? If you leave that blank, I can't do anything for you, right? Are we okay? We'll go to the next one. We got 5 questions total. Okay? I think 5. Okay, but wait. What if the force is acting at an angle relative to the object's displacement? So where it's going. Like for instance, if you guys see that picture there, right? Well, that's a different story. Right? You guys know if you see an angle, there's components involved. No matter what. You see an angle, got to break something into components. Okay? So, let's just have a look at this. So consider an object undergoes displacement d along a straight line under the action of a constant force F, which makes with an angle theta with the displacement. Okay, so if I were to draw the free body diagram for this, the dot would be the suitcase, I suppose. And straight down, we're going to have the force of gravity, obviously. And then to counteract the force of gravity, we're going to have that normal force. And then we're applying this FA force, F applied, right? And because it's at an angle, we have components. We have an X component, right? And we have a Y component. Here, let's just draw an arrow. And we have a Y component. Right? We know that the F applied in the X direction is FA cos theta. And we know that the FA in the Y direction is FA sine theta. Okay? So under these scenarios being ones like this, we can redefine our definition of work, because rewrite, I suppose, is maybe what it should say. Definition is still work. But we said that work is can only be attributed to the force being applied in the same direction as the displacement, right? So what that means is the Y has nothing to do with the amount of work in this question. Okay, it's only the X component that's attributing to the amount of work that force is actually able to do. Okay? And so if we were to rewrite this, let me change. We really only look at the X component of the force, okay, and the direction of the displacement. Okay, and so if I was to rewrite this, it would still be, it's still FD, but I'm interested in the X component of the force. And so if I were to rewrite this, I'd get work equals force cosine theta times the displacement. Okay, and the units are still Newton or Newton meters or joules, sorry. Okay, anybody have any problems before I go any further? Okay, so what I'd say is, like, this guy up here, he's applying a force, right? But really the only part of that force attributing to the object's motion or the work being done is the X component, right? The Y is not doing anything for him, aside from maybe decreasing the amount of friction. Okay, but that's a different conversation. Okay? So, there's no questions. I'm just watching the chat just in case. But example 3. An emergency worker applies a force to push a patient horizontally for 2.44 meters on a gurney with frictionless wheels. Okay, so part A wants us to determine the work done in pushing the gurney if the force applied is horizontal, okay, and has a magnitude of 15.5 newtons. Part B wants us to figure out, well, what if we change it and apply the force at 25.3 degrees below the horizontal? Okay. And part C just wants us to discuss the difference between those two scenarios, okay? And discuss the difference in the numbers that we see, okay? And so part A is relatively simple. If we apply the force directly to the gurney horizontally, we're going to see the amount of work that that force is actually able to do on the gurney, okay? And so we're going to see work is just equal to the force times the change in displacement, which is going to be the 15.5 newtons multiplied by the displacement of 2.44 meters, right? And what do we get? Well, we get 37.8 Newton meters, which would be equal to joules, right? Anybody have any problems with that? Now, part B wants us to look at what happens if we apply that force below the horizontal, right? Okay. Well, that's their equation. Oh, I missed the theta. Okay, so let's just find the work. We're going to apply the same force of 15.5, right? And the cosine of 25.3, right? How far did I push it? 2.44. And if you were to type that into your calculator, you'll see 34.2 Newton meters. Okay, as we go along here, I don't necessarily need to see this line anymore. We know that it's a Newton. I'm just emphasizing it, right? We know that work is measured in joules. Okay, energy is in joules. As we go further, okay. Any questions? So let's discuss then the difference in these numbers. Okay, we learned that when you apply when the force is applied at an angle, you only need to apply a component of the force to move an object in the direction of the displacement. Okay, so the work decreases. Okay, I'll write that down so it makes sense. Okay, so when okay. Okay, and we're talking about the work that the force is actually doing, right? Like so I think about this, and I was thinking about this morning. Sometimes, like I have an old car, and sometimes it stalls in the driveway, right? And if I were to like try and push that car back into the garage at an angle, it's going to be tougher for me to push it at an angle than if I push it straight on, applying the same force, right? And that's because if I apply the force at an angle, that strength of force that you are applying, you are losing some of it to pushing downwards. Okay? And so the amount of work that the force that you were applying is actually doing decreases because you're losing some of it to the y component. Whereas if you push on the horizontal, you're getting all of that force for the entire displacement. Okay, and so the amount of work that you're able to do is much higher because you're not losing any of the force to the y component. Okay, does that make sense to everybody? It took me a bit of time to wrap my head around that. It's like a combination between like you doing some work and the force doing some work for you. Okay. All right. If there's no questions with that, I'll jump down to do 4, okay? We're almost there. Okay. So a store manager raises an 8.72 kilogram case of cola at a constant velocity from the floor to a shelf. Okay. And the shelf is 1.72 meters above the floor. Later, a customer lowers the case 1.05 meters from the shelf to a cart at a constant velocity, okay? We want to determine the work done in each scenario here, okay? So I want to determine the amount of work that the employee had to do to lift the case in the first place to the shelf. And then we want to find, okay, well, what's the work done by gravity as the case rises, right? And keep in mind the employee we're going to call like the applied force, right? Like they're applying a force that's counteracting gravity. So that's the work. We want to find what amount of work that's doing. And then we want to find, lastly, the work that the customer is doing as the case descends. Okay. So I'm just going to draw a free body diagram here because I think it helped me in the conceptualization of it too. Okay, so I've got this case, should be relatively square, and on it we're going to have the force of gravity acting down, and then the person, right, the employee, has an applied force upward, like kind of like Fn, right, because it's a contact force. So there's this like applied force which we would call Fn because it's in contact with the employee's hand, right? Right, and that's balanced, and it's moving up at a constant velocity. So it's not like it's accelerating, and we have I don't want an E, I want a sum. Right, we still have sum of the forces is equal to 0. This is important for some of your, or one of the questions on formative 3. Okay, where we talk about this. If something's moving at a constant velocity, there is no acceleration. So if I were to rewrite this, ma, and we know that there's no acceleration, well, it's m times 0, right? And so sum of forces is equal to 0. That comes into play on the third formative, for those of you asking about that particular question when you get there, okay? So we still have the sum of the forces is equal to 0, right? And so we know that this force is equal and opposite to the force of gravity, okay? But this question isn't like, it's wanting us to solve for the work done. Well, the displacement was in the positive direction, right? Upwards to the shelf. And so when I look at part A here, when like we're trying to find the amount of work done by this force, right? Because that's the force that the employee is applying to the box of cola. Okay? And so because this force is acting in the same direction as the displacement, we can expect the amount of work to be positive, right? So when I look at this, work equals the force times the displacement. Both of these are going to be positive, And so our work, we should expect to see that it comes out to be positive, right? So work here is going to be equal to FA, right? But we know FA is equal and opposite to FG. And we know FG is MG, right? And so the applied force, right, or whatever's being applied, because if it wasn't equal, her hand would just go right through the box. So we know that it has to be mg delta d. But it's positive mg, right? Because it's acting in the positive direction. It's her hand on the box, the normal force. And so the work is the mass of the crate, 8.72, times 9.8, times the change in displacement, so from the ground up into the shelf, 1.72. And so the work will be 146.9 joules. Is everybody okay with that? The free body diagram helped me a lot this morning. Okay, and part B here, we know it's the same equation. Work equals the force times the distance, but this time we have the force of gravity, right? Because that's what we're interested in for part B. How much work is gravity doing, right? And so what we're going to see here is, well, we know the force of gravity is acting in the negative direction relative to the displacement, right, which is in the positive. So it's in the opposite directions, right, which means I'm going to get negative mg and times d. Okay, you're just going to plug it in. You're going to get the same number in terms of magnitude, but the work done is negative for gravity, right? Okay, and we're starting to formulate this right here, this relationship, or the relationship between these two questions, is formulating a relationship that we can put into words, right? So if the applied force acts in the same direction as the displacement, then the work done is positive. If the applied force, in this case gravity, acts in the opposite direction of the displacement, then the work comes out to be negative. Okay? Now, for part C, we want to know the work done by the customer as the case descends. So think here, the customer's got her cart, right? And we're taking the case of cola down from the shelf, and it's going to land in the cart, right? But the entire time that's happening, the customer is applying a force upwards. This is the force we're interested in. Okay, gravity is still acting down, but we're not asking about what's the work by gravity as the customer lowers. Right? This is not the question that we're asked. We're asked by the customer. So we're interested in the applied force of the customer, right? What's the displacement? Well, the displacement is coming down off the shelf, right? So if I look at this, the work is the force times the force applied times the displacement, right? Well, we know FA, the applied force, is equal to mg because it's equal and opposite to the force of gravity, right? But it's acting in the positive direction. So I got positive mg, but this time the box is coming from the shelf to the cart. So its displacement is going to be negative, right? Because we denoted at the very beginning of this question that the overall axes, up in terms of the y direction, up was positive and down was negative. We just didn't explicitly state that. Okay, so we know that the displacement, if the box is coming down from the shelf downward, well, the displacement must be negative. Okay, and we see, okay, well, mg in this question, it's the same mg, right? It'd be 8.72. right? And then we're going to multiply that by negative 1.05 because the displacement's negative. What do you get? Negative 89.7 joules. Right? The number's is less, right? The customer didn't have to do as much work for two reasons. One, she didn't lower it as far into the basket, or like into her cart. But two, the forces have kind of changed here, right? Almost, kind of. Actually, I think it's just the one reason, right? It's just the displacement wasn't as far. And I'm cluing into that now because if we look at the differences in these two questions, the only thing that has changed is the displacement value. Right? Is everybody okay? It can be a little bit tricky if we're, again, this is why I'm kind of like, it's nice I'm doing this for the first time because I don't take things for granted in terms of like conceptualizing things. It's been a long time since I've done some of this stuff, right? So I have to wrap my head back around it. Okay. Does anybody have any problems with what I've done there or questions? I'm going to summarize the positive and negative work thing here below in the note and add an extra layer. Okay. So positive work happens when the force applied, right? You'll see the word force applied the whole way, right? To an object is in the same direction as the displacement. Okay? Work is positive. Now, what's that mean? Well, let's just here for a sec. Let's write the, I'm going to try and find some room here. Let's suppose I wrote work is equal to F cosine theta D. Right? This was the equation that we wrote. So just as an extra layer for you guys, just to contextualize what's going on. If you guys think back to your unit circle, which we talked about yesterday a little bit, and I'm just going to draw 4 points here. You guys should remember these ones. Right? So we have cos 0, or cos theta, sine theta, right? And the answers here for 0 degrees, right? This is 0 degrees. If you were to plug in the cosine of 0 and the sine of 0, you should see this will be 1 and this will be 0. Okay? And then up here, I'll write these because this is important to what I'm about to write next. I'm just thinking, because I haven't done this in a while either. Up here, if we do the cos of 90 and the sine of 90, we'll see 0 and 1. And over here, this will be the cosine of 180 and sine of 180. Well, we're going to go -1 and 0. Okay, I don't really care about this one for right now. What you're going to see here is when work is positive, that means theta inside of here, theta is equal to 0. Right? So if I were to plug that in there, I get work equals F cos 0 D, which would equal FD, right? Because the cos of theta, or cos of 0 is 1. Okay? Negative work happens. This is me trying to add extra layers for you guys to understand and memorize this. Okay? Or at least conceptually lock it into your head. Right, I added this morning. Negative work is when the applied force is opposite to the direction. We just learned that. Displacement, sorry, opposite to the... Okay, so work is negative. What's that mean? Well, it means if I were to plug in theta equals 180 degrees, then we're going to see that it comes out, the F cos theta piece is going to come out to be negative FD, right? And the last one, zero work, when the force applied to an object is perpendicular, or when a force of displacement are zero. When force, or I think or, not of, force or displacement are zero, is zero, whatever. Okay. When is the force zero, you might ask? Well, if you actually have 0 newtons of force being applied, or in the instance where theta is equal to 90 degrees, right? Why? Well, if I wrote F cos 90 D, F cos 90, well, the cos of 90 is 0. So F times 0, that's equal to 0. There's no work done. Right? So we can't apply work if the force applied is perpendicular to the displacement. Okay, that gets to the y component piece. Doesn't really do a lot for you when we're looking at work, right? We care about the force that's being applied in the direction of the displacement, either positive or negative. Okay, that's what matters. The y piece doesn't do anything for you, which is why it's smarter to push something straight on, horizontal. So you're not losing any of that force to the y component. Okay, that's it for a push. Okay, I have one more question to do, and then you guys will be good to go. It won't take too long. Okay. This here just discusses like we can calculate the amount of work, and this is if this was a graph, right? If we found the area underneath of curves, much like displacement, right? If I found those areas, that would be the work area under a force displacement graph is work. That's all these are saying, okay? And if I wanted to solve for the total amount of work done and we had positive and negative works, we just add them up, okay? One more question, guys. One more. Okay, I'm going to start with a free body diagram for this question. So starting from rest, okay, a 5 kilogram block slides down a rough 30-degree incline that is 2.5 meters in length. Okay, and the coefficient of kinetic friction is 0.436. Okay, so here's what I got. Got this block, and I've got my incline that's not drawing straight lines. 30 degrees. Okay, and I'm just going to sketch out the free body diagram here, right? I've got the force of gravity acting straight down. I've got the normal force acting up, perpendicular to the incline. And the motion I know is going to come down the ramp. So why don't we say down the ramp is positive, right? Because the other reason why I like that is because I always typically make friction negative because it opposes the motion, right? And so I know if this thing's going to go down the incline, I like making friction negative, right? And so down the incline's positive, up the incline's negative, right? So the question is, okay, well, what's causing this thing to go down the incline? Well, it's this X component. Let me just draw the components. We've got a Y component of the gravity, right, as usual. And I have the X component of the gravity, as per usual. What's causing the motion? Well, if I tilted my axes like what I've done, right, I got positive Y up here and negative Y down here, then the forces acting in the X direction are what is causing the box to move down the incline. Well, I only really see two forces acting in my X direction, left and right. I see this X component of the gravity, which we know as being mg sine theta, and I know the Y component is mg cos theta. Okay, and what I want to find is I want to find the first part here, the work done by the force of gravity. I won't do that in red or in blue. I'll do it in red, right? Because the force of gravity is doing some work, right? But remember, its perpendicular component is not doing any work, right? And so the piece of the component of the gravitational force doing work in this problem is mg sine theta, because it's what's causing the block to go down the incline, right? So if I look at solving this part A, you're still going to have work equals force times distance, but which force am I interested in? What's the X component of gravity, right? The mg sine piece. So work is equal to mg sine theta multiplied by the distance that the block's going to ultimately travel, right? Or the displacement, right? And the displacement is going to be positive because we've defined it to be positive. Starting at the top, it's going to the positive direction, okay? And so we're going to get D, right? You just throw in the numbers. 9, oops, I need the mass. Mass is 5 times 9.8 times the sine of 30 times D, 2.5. And the work here, if you type that all in, you're going to get 61.25 joules. That's the amount of work that the force of gravity has done to move this block from here to here, 2.5 meters. Okay. Okay. Part B, the work done by the frictional force. Well, the frictional force goes up the incline, so it's negative, right? It's negative, but the block's still going down the incline in the positive direction. So we better expect that the force of friction is acting in the opposite direction to the displacement. And so we better expect to see a negative work value come out because it's opposing that object's motion, right? And so if I look at part B, it's still work equals force times distance, right? Except this time, we want the force of friction, right? Well, you guys know that the force of friction is the coefficient multiplied by Fn. Well, Fn, what is Fn? Fn is equal and opposite to the Y component of gravity, mg cos theta, right? And so the force of friction is equal to mu mg cos theta. That's where this comes from. Right? And so that's what you plug in. This is your force. How long was that force applied for? That's the displacement, 2.5. So you go mu mg cos theta times the displacement. Throw in your numbers. 0.436. There's lots of them this time. 5 times 9.8 times cosine of 30. I'm going to move this. Give me a sec. Times 2.5. And you type that in your calculator, you're going to see you should get a number of negative 46.25 joules. And if I really wanted to find out the total amount of work done on that box, I could add these two numbers together. right? Because you had a force opposing the motion, that was negative work, and you had a force in the positive direction, that was attributing work, right? Or work done. So if you wanted to figure out the total amount of work done on this system, you could add those two numbers together. That would give you an answer. Okay, I didn't ask that. What I did ask, work done by the normal force. Well, the normal force, Fn, makes an angle of 90 degrees with the incline, right? Right? And so if I were to type that in, the force that's being applied there, if I wanted to do this work, we know that the force here is applied at a perpendicular angle. So F cos 90 times the displacement. We know that the cosine of 90 is 0. So what do we get? We get F times 0 times D equals the work. Well, we know that the work here, because the force is perpendicular, is 0 joules. Okay? That perpendicular force, or force in the y direction, cannot do any work in the motion of that object. Okay? It does nothing for you. Okay? It might actually even probably make it harder because you're going to increase friction in those kind of questions, right? If it wasn't Fn. Okay? Does anybody have any problems, questions, comments, concerns? If there is anything you don't agree with, you can let me know.